Millions of tons of steel get forged worldwide every year, but only a handful become true mechanical titans. Picture a part weighing 30 tons. That's like 10 adult elephants compressed into a single ring. Here's the paradox. This behemoth must be machined to within a micron, thinner than a human hair. One of these bearings costs up to $3 million, and if it fails, the losses hit tens of millions. How do you make a steel monster perform with Swiss watch precision under thousands of tons of pressure? Stick around till the end, and I'll reveal the secret engineers keep hidden. What actually happens to metal when it gets shocked in oil? And why, without one critical step, this 30-ton beast will shatter like glass? You've never looked at metal this way before. I'm standing right now next to what will become a bearing for a tunnel boring machine shield. This is a steel ring 26 feet in diameter, weighing around 30 tons. And here's the most amazing part. This massive thing needs to be machined to within 0.02 of an inch. That's thinner than a human hair. Let's start from the very beginning, with material selection. For bearings like these, they choose special alloy steel or similar alloys. This steel contains chromium, molybdenum, and other alloying elements that make it super strong and wear-resistant. Interesting fact, Chinese engineers developed an improved version of this steel specifically for 26-foot bearings, the largest in the world. The first stage of production is forging. Steel blanks are heated to 2,000 degrees Fahrenheit and forged under massive presses applying thousands of tons of force. The forging process aligns the metal's grain structure, making it stronger and more uniform. Here's a press as tall as a 3-story building that came down on red-hot steel with enough force to flatten a bus. After forging comes rough turning, enormous lathes, some the size of a 2-car garage, machine the blank, shaping it into a ring. The cutting tools for these lathes are made from tungsten carbide, a material 10 times harder than regular steel. Even so, these cutters wear out after just a few hours of work. Now for the crucial stage, heat treatment. This is what transforms ordinary steel into a nearly eternal material. The bearing ring is loaded into a giant furnace and heated to temperatures between 1550 and 1650 degrees Fahrenheit. At this temperature, the crystal structure stabilizes, ready for the next shock. Then comes quenching, the most dramatic moment in a bearing's life. The red-hot ring gets rapidly cooled by plunging it into an oil bath. The temp drops from 1600 to 300 degrees Fahrenheit in a matter of minutes. The oil hisses, boils, creating clouds of vapor. This sharp temperature shock transforms the steel's internal structure into martensite, a super hard crystalline form. But hardened steel has a problem. It's brittle as glass. One hit, and the multi-ton ring could crack. That's why the next step is tempering. The bearing gets heated again, but this time only to 350 to 500 degrees Fahrenheit. It's held at that temperature for 4 to 8 hours, then slowly cooled. Tempering reduces internal stress, makes the steel less brittle, but keeps the hardness. After heat treatment, the bearing has to go through rigorous inspection. They use ultrasonic equipment that can find an internal crack smaller than 8 inches. They also check microstructure samples. They take small pieces of metal and look at them under a microscope. You need 100% martensite with no retained austenite. Now begins the most precise stage, precision grinding. This is what separates a simple steel ring from a high-precision bearing. Look at this grinding machine. It's a specialized piece of equipment that costs several $1 million. The abrasive wheel spins at 5,000 revolutions per minute, removing microscopic layers of metal. Grinding happens in multiple stages. First comes rough grinding, which removes about 1/10 of an inch of material. Then finish grinding, which works to within 5 microns. Each pass of the grinding wheel is monitored by laser sensors that measure material thickness in real time. But that's not the end. After regular grinding comes super finishing, a process that makes the surface incredibly smooth. They use fine-grained abrasives and special techniques that reduce surface roughness to fractions of a micron. Under a microscope, this surface looks almost like a mirror. Why is this precision critical? Because these bearings operate under incredible loads. Take a tunnel boring machine, a beast that chews through solid rock. The cutting head, 57 feet in diameter, spins as it tears into granite. The force acting on the bearing reaches thousands of tons. If the bearing surfaces are uneven, even by a few thousandths of an inch, stress concentration zones appear. Metal at those points starts wearing down, heating up, and the bearing will fail. For large bearings, a segmented design is often necessary. A bearing over 30 feet in diameter can't be made in one piece. It simply won't fit in any heat treatment furnace. So they're made from separate segments, each machined individually, then all joined together with micron-level precision. The joints between segments must be so precise you can't even feel them with your finger. Interesting detail, for wind turbine bearings, they often grind a special profile called a crown. This isn't a decorative element. The crown distributes the load so maximum pressure falls on the center of the bearing, not the edge. If the load concentrates at the edges, premature wear occurs. The crown might be only a few thousand inches tall, but its shape is calculated by sophisticated computer programs. Let's talk about scale. One company, Rote Erde, manufactured over 2,500 bearings for tunnel boring machines in 3 years of operation. Each one unique, engineered for a specific machine and geological conditions. The cost of a single bearing ranges from $500,000 to $3 million depending on size. Sounds like a lot? Now picture this. If a bearing fails deep inside a tunnel, repairs can cost tens of millions and halt construction for months. The service life of these bearings is measured in decades. A wind turbine bearing must run for at least 25 years, generating millions of rotations. A bearing for a tunnel boring shield can chew through 15 miles of solid rock, spinning day and night for 3 to 4 years. Quality control here is absolute. Every bearing gets checked on a coordinate measuring machine, accurate to 200 thousandths of an inch. It's a room-sized machine operating in a temperature-controlled room, plus or minus half a degree Fahrenheit. Why such precision with temperature? Because steel expands when heated. Temperature swing of just 2 degrees can change the bearing size by several thousandths of an inch, enough to ruin all measurements. They also run fatigue tests. They take metal samples from the very first batch and cyclically load them millions of times, simulating years of operation. If a sample fails before the calculated lifespan, the entire batch gets rejected. Harsh? Yes. But there's no other way. Billions of dollars in investments and human safety are on the line. The coolest thing about all this, the combination of gigantic size and incredible precision. It's like building a clockwork mechanism the size of a house. A part weighs a ton, but has to be accurate to within microns. A deviation you can't see with the naked eye can destroy the entire structure. And to keep my channel from falling apart, I'm counting on your comments and subscriptions. Subscribed? You sure you subscribed? And now? Alright then, let's continue. Engineers are constantly improving the technology. Right now they're testing new coatings for bearings, nanostructured films just a few microns thick that can double their lifespan. They're also developing sensors built right into the bearing that monitor temperature, vibration, and wear in real time. These smart bearings can warn you about a problem a month before it fails. Every year, the world produces over 1,800,000,000 tons of steel. But only 27,500 tons of it became part of a roof that moves like a camera shutter. 8 pedals, 500 tons each, open the sky above 70,000 spectators every single day. Tolerance, less than 2 millimeters. One mistake, and 500,000 kilograms go off the rails. How did 3 dozen factories across 4 time zones assemble this mechanism with zero room for error? Stick around till the end, and you'll find out why this roof nearly broke the biggest steel producers in America. 27,500 tons. That's the first number you need to wrap your head around. That's how much steel went into this stadium. More than 2 aircraft carriers. 4,000 tons of that? That's just the moving roof. 8 pedals, each weighing about 500 tons. Together, 2 million pounds of steel opening and closing every single day above 70,000 fans. The company that built all this? Containment Group, headquartered in Quebec, Canada, one of the biggest structural steel manufacturers in North America. But even for them, this contract was something totally new. When the scale got so massive that no single plant could hit the deadlines, Containment did something unprecedented. They split production across nearly 30 factories throughout North America, from Quebec to Texas, from Ohio to Carolina. 4 time zones, thousands of people, one project. It all started with architect Bill Johnson from HOK. In 2013, he won the design competition with an idea that, according to the engineers themselves, made them go pale. A roof oculus that opens like a camera shutter, 8 triangular pedals moving along diagonal tracks, sliding toward the perimeter to reveal an oval opening directly above the field. The inspiration. The Pantheon in Rome. The same one that's 2,000 years old. Except here the opening isn't static, it moves. And it's not made of stone, but 4,000 tons of steel. The engineers at Buro Happold, who were entrusted with the structural solution, immediately saw the problem. A traditional retractable roof? That's 2 halves moving in opposite directions. Simple, predictable, reliable. But 8 independent pedals moving diagonally, each one differently, all simultaneously and somehow forming a perfect sphere when closed? This wasn't an engineering challenge. This was a moon landing level puzzle. I climb onto the roof and walk right up to one of the pedals in its open position. There it is, lying quietly at the perimeter. 500 tons of steel that looks almost delicate. But everything I'm seeing is just the shell. Inside, there's a whole architecture. Each pedal is held by 3 main trusses. These trusses taper from 30 feet high at the base down to literally 3 feet at the tip. Why? Because the pedal is a cantilever. A cantilever stretching anywhere from 196 to 232 feet that, when closed, hangs over the center of the stadium, supported only at one end, like a giant fishing rod suspended over open sky. The closer you get to the free end, the less material you need, because the load there is minimal. It's pure structural logic translated into form. The pedals come in 4 sizes. The stadium's oval, so each pair of opposing pedals has its own unique proportions. The widest? 160 feet. The narrowest? 128. No 2 are the same. This is where Containment comes in. The company's factories received 3D models of every single component from the digital BIM model of the entire stadium. Absolutely everything was modeled. The position of every bolt, every weld seam, every connection angle. Before the first sheet of steel was cut, everything existed digitally, accurate to a 1/16 of an inch. Why is this level of precision critical? Here's the answer. Each pedal travels on tracks, and the tolerances between the runner bogie and the track. 1/16 and even 1/32 of an inch. That's less than 2 millimeters. Less than the thickness of a fingernail for a structure weighing 1 million pounds. Lead project engineer Bill Darden said in an interview, "We were literally discussing 1/16 and 1/32 of an inch at roof meetings." Picture it. Engineers, builders, manufacturers gathered together arguing about 0.5 millimeter. Because in a mechanism at this scale, an error the size of a 32nd of an inch could mean a pedal derails 305 feet above the field. JGM, a Containment subcontractor, fabricated over 3,000 tons of nodes, beams, box trusses, and vertical columns. Every single part, after fabrication, underwent 3D scanning, a laser checking whether real dimensions match the digital model to within hundredths of an inch. Any deviation? The part gets sent right back to production. Now, the most interesting part, the mechanics. How does something this massive even move? Each pedal rides on 2 parallel rails. The inner rail is the drive rail. It carries the bogies that pull the pedal. The outer rail is the stabilizing rail. It keeps the tip of the pedal from lifting. Remember the cantilever? When the pedal moves and the tip hangs out over the center of the stadium, it has a tendency to fly upward from its own eccentricity. The outer rail, that's what holds it down. The bogie is a mechanism on 8 metal wheels that roll along a track. Each bogie is powered by 12 electric motors rated at 7.5 horsepower each. That's 90 horsepower per pedal. Multiply by 8, the roof moves with 720 horsepower. And this system, this is why it's brilliant, isn't just on/off. The Unisystem software controller tracks the position of each of the 8 pedals independently in real time and adjusts the speed of each motor so all 8 reach the endpoint simultaneously. Because the pedals are different sizes, they travel different distances along different trajectories. If you let them move at the same speed, one arrives early, another runs late, and the whole system collides. So the algorithm constantly dances with the speeds, dynamically balancing 8 independent mechanisms into one synchronized motion. The result? A camera shutter the size of a stadium. Each pedal moves in a straight line, but the geometry of the rails and the relative motion of adjacent pedals create the illusion of rotation. Spectators below see it spinning, even though no part is actually rotating. Opening and closing, 8 to 10 minutes. The push of a single button. A small detail that reveals the scale of engineering paranoia on this project. When the pedals are stationary, what keeps them from moving on their own? For example, under asymmetric snow load or during gusty winds. On each pedal, 2 rail locks. They automatically engage the rail when the system isn't operating. It's a parking brake for 500 tons. Until the locks are released, no motor in the world can budge a pedal. This isn't excessive caution, this is engineering culture, where every failure scenario is thought through in advance. Assembling the roof on the construction site? That's a whole other saga. Each pedal was put together on the ground as a single structure, then hoisted by cranes to a height of 305 feet. One crane couldn't handle it. They used a tandem. The moment when one pedal slowly rises up and for a second blocks out the entire sky over Atlanta, that's a shot that stops your heart. 500 tons of steel hanging between heaven and earth, and 200 people below holding their breath. After the lift, precision installation onto the rails. The tolerance, remember, 1/32 of an inch. Riggers with laser total stations guide the pedal into position, inch by inch until the bogies sit on the rail perfectly. One pedal, one day's work. The roof delayed the stadium opening 3 times. They'd planned for March 2017, opened in August, 5 months late. Conam itself, after this project, officially announced it would no longer take on the role of steel contractor for complex and large-scale projects. This project cost them way too much, not in money, but in nerves, logistics, and resources. And subscribing to my channel? Free. Have you done it yet? Total stadium budget, $1.5 billion. How much of that was the roof? Never officially disclosed, but everyone in the industry says hundreds of millions. Some estimates around a quarter of the budget, just for the moving roof mechanics alone. I'm standing on the rail platform watching a pedal start to move. 12 motors quietly spin up. Locks click and release. 500 tons glide forward without a sound. No squeak, no shudder. Just smooth, confident motion. Like a clockwork mechanism the size of a city block. Arthur Blank was right. This is the most complex roof in history, but it's also the most beautiful. When all 8 pedals pull back to the perimeter and Atlanta opens through an oval hole in the sky, that's when pure engineering becomes art. 55 million pounds of steel, 3 dozen factories, 4 time zones, thousands of people. And the result is something that didn't exist anywhere in the universe before 2017. 8 steel pedals, 1 clockwork mechanism, endless sky. There's a metal that doesn't rust, doesn't age, and doesn't disappear. It just waits. Waits in water, in air, and even in our homes. What if I told you this metal spent centuries helping humans extract gold, fill cavities, and measure temperature, but at the same time slowly drove them insane and killed entire cities? Mercury, liquid silver, looks almost magical, but hides one of chemistry's most dangerous secrets. It can't be destroyed, it can only be hidden. And if you watch this video to the end, you'll find out where humanity is hiding Mercury forever today, and why one mistake could bring it back into our lives. Mercury's story doesn't begin with shimmering droplets, but with a bright red mineral, cinnabar. For thousands of years, people used cinnabar as a pigment. Ancient Chinese and Romans made vermilion paint from it, decorating temples and statues. But cinnabar mining always came with tragedy. Workers in the mines suffered from mysterious tremors, delirium, and early death. The process of extracting pure mercury from cinnabar is pretty simple. The mineral is crushed and heated in special furnaces. At 675 degrees Fahrenheit, mercury vaporizes, then condenses as heavy silvery droplets. This ease of extraction made mercury accessible but also dangerously available. One of the most widespread uses of mercury in history was extracting gold and silver. Mercury has a unique ability. It instantly wets other metals, dissolving them and creating alloys called amalgams. During the gold rush era, prospectors mixed crushed ore with mercury. Mercury, like a magnet, pulled the tiniest gold particles from the rock, forming a thick paste. To get pure gold, they simply heated the amalgam over an open flame. The mercury evaporated straight into the air people were breathing, leaving pure gold at the bottom. This method, known as amalgamation, led to devastating contamination of rivers and soil across the globe. Even today in the Amazon jungle, illegal gold miners use tons of mercury, poisoning ecosystems for decades to come. For a long time, mercury was considered irreplaceable in science and everyday life. In thermometers, mercury expands uniformly when heated, making it the perfect working fluid for precise temperature gauges. Mercury switches worked flawlessly for decades because liquid mercury conducts electricity beautifully and doesn't wear out. Amalgam fillings made from a mixture of silver and mercury were the standard in dentistry for over 100 years because of their incredible durability. But there was a dark side. In the 19th century, mercury was used to treat fur in the making of felt hats. Craftsmen constantly inhaled mercury vapors, which attacked their nervous systems. That's where the phrase "mad as a hatter" came from, immortalized by Lewis Carroll in Alice in Wonderland. The symptoms of poisoning, confusion, memory loss, and tremors became an occupational disease of entire industries. Mercury's real danger lies in its ability to bioaccumulate. When mercury enters water, bacteria transform it into methylmercury, an incredibly toxic organic form. It builds up in plankton, then in small fish, and finally, in large predators like tuna or sharks. A person eating that fish gets a massive dose of toxin. The most horrific example, the tragedy in the Japanese city of Minamata in the 1950s, where a chemical plant dumped mercury into the bay. Thousands died or were left disabled from brain damage. This event gave rise to Minamata disease and forced the world to consider banning the metal. Today, the Minamata Convention is in effect, signed by over 140 countries. It bans the production and export of mercury thermometers, pressure measurement devices, most types of fluorescent lamps, and the use of mercury in many industrial processes. If you break a mercury thermometer at home, it's a small-scale ecological disaster contained within a room. The mercury shatters into countless tiny beads that roll under baseboards and deep into carpet fibers. At around 70 degrees Fahrenheit, they start evaporating actively. One tiny mercury bead can poison the air in a closed space for months. Mercury vapor has no smell or taste, making it an invisible killer. Since mercury can't simply be burned or dissolved without a trace, it's a chemical element that doesn't break down. The only solution is complete removal and containment. It all starts at specialized facilities where millions of spent fluorescent bulbs, old medical devices, and industrial sensors end up. The first stage is mechanical shredding. For example, bulbs enter a sealed shredder that crushes the glass, aluminum bases, and mercury coating into fine debris. This mixture looks like trash, but it's extremely toxic, because every ton of this debris contains several pounds of mercury. By the way, mercury is incredibly heavy. A 1-liter bottle of mercury weighs more than 28 pounds. If you tried to lift a bucket of mercury, you'd be lifting 300 pounds. That's like 2 grown men. Next comes the main process, thermal desorption under vacuum. This mixture gets loaded into massive steel furnace reactors. The key feature here is the vacuum itself. When we pump out the air, mercury's boiling point drops. The furnaces heat the mixture to temperatures between 570 and 750 degrees Fahrenheit. Under these conditions, mercury starts evaporating intensely, separating from the glass and metal scrap. The vacuum system pulls out these toxic vapors, giving them zero chance to leak out into the workshop air. Next, the mercury vapor enters the condensation system. These are long coils cooled to low temperatures. As soon as the hot vapor touches the cold walls, it transforms back into liquid metal. Silvery droplets trickle down into special collection tanks. What comes out at the end is pure recycled mercury. However, since the world is gradually phasing out its use, this metal no longer returns to factories. The final stage is permanent imprisonment. The liquid mercury is mixed with special reagents like sulfur to convert it into a solid and stable compound, mercury sulfide, which doesn't evaporate and doesn't dissolve in water. This substance is sealed in thick-walled steel containers, which are then coated with an anti-corrosion layer on top. These containers are shipped to underground storage facilities located hundreds of feet deep in abandoned salt mines or granite formations. There, in complete dryness and monitored by sensors, mercury is stored for decades. It's the only way to guarantee that liquid silver never reaches groundwater and doesn't come back to us through fish or water. Disposal is expensive and complicated, but it's the price humanity pays for the safety of future generations.